What if I told you that multiplication can make things rotate? I don't mean this as some metaphor, not as some clever analogy. I mean physically rotate vectors. Now, multiplication on its own doesn't have this power. You need I alongside it. In fact, multiplying a number by I actually rotates it exactly by 90 degrees. And once you see why with a bit more precision, complex numbers start to look very different from the strange collection of rules you may have first met at school. Because I isn't just some weird number whose square is -1. It's a much deeper concept rooted in geometry behind all the complex arithmetic. Let's start with the one thing we know about I squared equals -1. That tells us that if we multiply I by itself, we get -1. But let's look at what happens if we keep multiplying by I. Start with 1. Multiply by I, and we get I. Pretty straightforward. Multiply by I again, and we get -1, simply from the definition. And again, but this time, we get -I. And once more, we're back at 1. So we have this strange cycle going on here. Now, algebraically, there's nothing particularly mysterious about this, but geometrically, it looks remarkably like we've gone around a circle. So maybe there's a better way to understand what's happening. Let's add a visual backdrop to this investigation, the Argand diagram. We have the real axis going horizontally and the imaginary axis going vertically. Now 1 is a number on the real axis, and here is a vector arrow pointing at 1. Now if we multiply this by I, that vector moves anti-clockwise 90 degrees and points at I on the imaginary axis. And once again, it's at -1. And once again, it's at -I. And one last time, we're back at 1 again. Now let's put that to one side. A complex number looks like this: A plus BI. It has a complex part A and an imaginary part B. Instead of thinking of it as a strange combination of two types of numbers, we can use those two numbers as coordinates. The real part goes horizontally, and the imaginary part goes vertically. So 2 plus 3i becomes the point 2, 3. And now something quite interesting has happened here. A complex number isn't just something we can calculate with. We can see it, which is far more powerful. We can either think of it as a point or as a vector represented by an arrow from the origin. So let's take our visual vector representation of 2 plus 3i and ask the question we're really interested in. What happens when we multiply it by I? We will first calculate it algebraically and then visualize it geometrically. So I times 2 plus 3i, when expanded, becomes 2i plus 3i squared. And because I squared equals -1, that becomes 2i minus 3. If we rearrange this, we get -3 plus 2i. This complex number has coordinates -3, 2. So our original point, 2, 3, has now become -3, 2. And here's where things get interesting. Now consider the vector 2, 3 and rotate it 90 degrees anticlockwise. Where does it land? Exactly at -3, 2. So that means multiplying by I has just rotated our vector by 90 degrees. But perhaps this is just a coincidence. Maybe it only worked for 2 plus 3i. So let's take another number. Take 1 plus 2i. So we can visualize the vector like this using the coordinate 1, 2. Multiplying it by I, we get I times 1 plus 2i, which equals I plus 2i squared, which simplifies to -2 plus I. So the coordinate 1, 2 goes to -2, 1. Again, that's exactly a 90-degree rotation. And we can keep trying numbers. Every time, the same thing happens. So there has to be something deeper going on. The stronger way to prove this pattern is using an arbitrary complex number a plus bi, where a and b are real numbers. If we multiply it by I, we get I times a plus bi. This expands to ai plus bi squared. Replacing I squared with a -1 and rearranging, we get -b plus ai. So multiplication by I takes a plus bi and turns it into minus b plus ai. In terms of coordinates, that's ab go into minus b, a. And that happens to be exactly the rule for for rotating a point 90 degrees anti-clockwise. So this isn't just a coincidence, we've actually just proved it. Multiplying by I rotates a complex number by 90 degrees. But now we've got a new question. Why? Why should multiplication of all things have anything to do with rotation? Let us look back at our definition, I squared equals negative 1. Now consider a similar expression, x squared equals 4. So we want a number that when multiplied by itself equals 4. And that number is 2. Pretty straightforward. Now let us think a little outside the box. Imagine x is an operation that when performed twice is the same as scaling or multiplying by 4. Well, that means x is the operation scaled by 2. And we can visualize this. A 1 by 1 cube becomes a 2 by 2 cube when scaled by 2, and then a 4 by 4 cube when scaled by 2 again. And notice that this is the same as scaling a 1 by 1 cube by 4 in the first place. Now this is the secret intuition that we need to really understand what I is. Now let's come back to I squared equals negative 1. Let us replace the I with an x. Now using the same logic as before, we want an operation that when performed twice is the same as scaling or multiplying by negative 1. And that is simply the rotation anticlockwise by 90 degrees. And hence, multiplying by I is the same as rotating anticlockwise by 90 degrees. Let's visualize this to understand it a bit better with our helpful friend, the Argand diagram. So we have the vector 1 on the real axis. This vector goes to I after rotating anticlockwise by 90 degrees once, and then goes to negative 1 if rotated again anticlockwise by 90 degrees, satisfying our definition from before. Mathematical progression happens when we think of ordinary operations from outside the box, just like how we thought of multiplication not just as scaling, but as a rotation, which made it much more powerful. Here's a question for you to try, and put the answers in the comments section down below.
Hey, if you're still here, don't forget to like, share, and subscribe to our YouTube channel. Help us grow. Thanks for watching, and see you next time at Delta Instinct.